Right, so this section is about conditional probability. And a conditional probability, if we just jump right into the definition here, a conditional probability is a probability that of an event occurring if you already know another event has occurred. It's conditional. And this is a very useful concept because this happens all the time, right? Like sometimes you might say, well, this has a chance of happening, and then given you no information, it changes. For example, if you let's say you hear yesterday the chance of rain tomorrow is 50%. And then the next day you walk outside and then you see that it's very cloudy and gloomy. And you can almost say with certainty, well, now the chance of rain is much more than 50%, right? Because given that the event has occurred, that I already see, this cloudy and gloominess outside, the probability changed. So now what's the probability it's going to rain? You might say it's more like 90%. And that is what a conditional probability basically is. And to denote a conditional probability, we write the probability of B given A. So this vertical line is read as a given. Okay, it's not a division sign or anything like that. It just means the probability given A. So we want to find the probability of B given A. So A is the event that has already occurred. You write that actually second in the parentheses after the line. And then we want to find the probability of B. So we're going to find some conditional probabilities from what we call a two-way table. And in this two-way table, it says a sample of 146 families in the United States was asked if they own a computer and if they will be taking a summer vacation this year. 57 families own a computer, 101 will be taking a summer vacation, and 46 families own a computer and will be taking a summer vacation. So in a two-way table, one variable, summer vacation, and just so we're all consistent, I'll put summer vacation at the top, okay, and computer on the left. You could switch these. There's nothing that says they can be one way or the other. It's just the table's going to look a little different. So it's better if you do the same thing that I'm doing. So we have yes summer vacation, no summer vacation, yes computer, no computer, and we have a total. Column and row. So we want to put the numbers in this table where we, based on the information that we have. So read the information again and then try to put the numbers in the table and see if you get the same thing I get. So when you put the numbers in the table, you should have gotten, it says there's 146 total families. So that is 146. And then it says 57 own a computer. Now, if 57 own a computer, that is the total of people that said yes for computer. That's how we read the table, right? So it doesn't go here or here, the 57, because we don't know anything about those people that are taking a summer vacation or not. Those are just 57 total families that actually own a computer. 101 will be taking a summer vacation, and then 46 families will be doing both. And now we can fill in the rest because the columns and rows should add to the total column and row. So for example, I can put 11 here because 46 plus 11 is 57. 55 goes here because 46 plus 55 is 101. 45 goes here. I said 55. I meant 55. 101 plus 45 is 146. And then 89 goes here. And then the middle number is 34. And to double check we did all this correctly, it should work both ways. So 55 plus 34 is 89. And 11 plus 34 is 45. So that all works out. Okay, and that's our table. And from this table, we can calculate some probabilities. For example, the first probability is find the probability that a randomly selected family is not taking a summer vacation. And let's use the symbol S. Let's use the symbol S for summer vacation. And let's use the letter C for computer, just so you know what I'm talking about. So if we want to find the probability someone is not taking a summer vacation, in the last section we learned that S prime, this is not a 1, it's a prime, is how we can denote not, or the complement of an event. So you are taking a summer vacation or you're not taking a summer vacation. Those are the only two options, right? So if I put S prime, that means not taking a summer vacation. And what's the probability of selecting this person? Well, I always like to think of the denominator first when it comes to probabilities. And there's 146 people total for me to select from. And from those people, there are 45 that are not taking a summer vacation. So the probability is 45 out of 146, which is approximately 0.3082. Let's do the next one. Find the probability that the family owns a computer. So think about this one on your own before you see my solution. And it's very similar to the last one. So 146 is the total. And then how many people own a computer? Well, that's 57. And so the decimal approximation for that is about 0.3904. So about a 39% chance. All right, find the probability that the randomly selected family is taking a summer vacation given that they own a computer. Now, this one has a given, so you have to be able to write this correctly. It says we want to find the probability the family is taking a summer vacation. So this is what we're trying to find the probability of, and we're given they own a computer. So summer vacation given they own a computer. Okay. And in probability problems, when you read a probability, it's very important to understand completely what the question is asking, because the one word, one small word, can make a difference. And often it's words that we're not used to, or we're used to just glimpsing over. But in a probability problem, it's very important you understand. So since we're given they own a computer, we are only looking among the computer individuals. Therefore, we're not looking over 146. How many people actually own a computer? Because that's what we're given. Well, 57 people own a computer. So that's our denominator now, because now we're only selecting among the people that own a computer. And of those 57, 46 have gone or will go on a summer vacation. So all we're doing is looking at this row here. 57 is the number of people who do own a computer, the 57 here, and we are just looking at the 46 of the 57, not the 146, because again, we're given that they own a computer. Find the probability a randomly selected family is taking a summer vacation this year and owns a computer. So S and C. So are we given anything in this one? And we're not, right? We aren't given anything. So our denominator is 146, and our S and C, the number that are taking a summer vacation and own a computer, is 46. So 46 out of 146. And I forgot to give my decimal approximation for the previous one, so I'll do that now. This is 0.8070, and this is 0.3151. So notice that, this is really, if you look at part C and D, the problem is almost identical. The only difference is this word given and the word and, pretty much. And very often in reading we skip over the word and because it's just a conjunction. It doesn't really have a lot of meaning in a sentence itself. But the difference here is very important. And later in section 3.3, when we talk about the addition rule, that'll use the word or, and it's very important to just be able to distinguish between the words given, or, and. Okay, so that is basically conditional probabilities from a two-way table. Next, we're going to talk about conditional probabilities that are from independent events and dependent events. So basically, if events are independent, they don't affect each other. If events are independent, then if one event occurs, it doesn't affect the probability of the next event. So for example, let's go back to our weather thing. Let's say, we hear on the radio, or we look at our weather app and it says there's a 50% chance of rain tomorrow. And then tomorrow we get up out of bed and we see that there are 5 pairs of black socks in our sock drawer. Well, given that there are 5 pairs of black socks in our sock drawer, what's the probability it's going to rain? Did that change the probability from the previous day? No, we would pretty much say it's still 50%, because why would the black pair of socks in my sock drawer affect or be related to how many or how much rain, or if it's going to rain or not that day, right? Those are totally independent. Something else that's independent. Let's say I flip a coin and I get heads, and I flip another coin and I get heads. What's the probability that I flip a coin and get heads the next coin flip? Well, if I got heads the first time and I got heads the second time, probably I get heads the third time? Well, that's still 50%, right? The probability of getting heads the third time is still 50%, because why would the first 2 coin flips affect the third one, right? You could get heads 100 times in a row, and as long as you are sure that that is a fair coin, you would still say the probability of heads is 50%. Now, that's not always the case, right? Like if you got heads 100 times in a row, you probably think it's not a fair coin. But you get what I'm saying, okay? So independent means they don't affect each other. And because they don't affect each other, the probability of B given A is equal to the probability of B, and the probability of A given B is equal to the probability of A. And this means that we don't care that B has happened. We don't care that B has happened. We just care that if B has happened, well, the probability of A is still the same. That's all this says. This is just a mathematical way of writing it. And events that are not independent are dependent. So I want you to read these problems here on your own. Pause the video here and see if you can come up with them being independent or dependent. So hopefully you paused the video and you came up with if they're independent or dependent. So the first one is dependent. And the key to this one is we're not replacing the block. So if you have 5 red blocks, let's actually write this out, 4 blue, and 3 white. And if I take a white block out, so I remove one and I don't put it back, well, now the probability changed, right? It changed because I have less blocks to choose from, so the probability is effectively different. What about tossing a coin, getting a head, and then rolling a 6-sided die and obtaining a 6? So if I toss a coin and get a head, and roll a 6-sided die and obtaining a 6, that is independent, right? Because why would the coin toss affect the die roll? Why would the coin toss affect the die roll? They wouldn't. They're independent of each other. What about texting while driving and getting in a car accident? I hope everybody said dependent for this one, because we all know, or we should know, that if you text while drive, then you are more likely to get in a car accident. This happens all the time. So you shouldn't be looking at your phone when you're driving, kids. Make sure that you are put your phone away, put it in the back seat if you need to, and then get it out when you are done driving. Okay? Okay, and then selecting a king from a standard deck, replacing it, and then selecting a queen. Well, this is independent, and the key here, why this is independent, is we're replacing it, right? So with replacement is independent, and if we go back to the first problem, not replacing is dependent. And that's because if you replace it, it's like nothing's changed. And the probability of drawing the queen will be the same as if you drew the king and replaced it, or if you didn't draw the king at all. Because if you put it back and you replace it, then you are not drawing. If you put it back and replace it, that's like you're not drawing the king at all. Okay, so that's the difference between independent and dependent events, and that's important for our multiplication rule, because our multiplication rule says the probability of A and B. So this is the probability that if 2 events occur in sequence, we take the probability of A and we multiply the probability of B given A. And if they're independent, we still take the probability of A, but we multiply by the probability of, well, if they're independent, what's the probability of B given A? And we talked about independent means the probability of B given A is equal to the probability of B. This is what we just talked about on the previous page, because we don't care that A has occurred. The probability doesn't change. So if they're independent, we don't need to worry about that. So basically, if you want to find the probability that two events occur in sequence, you find the probability of those individual events and you multiply them, right? Given that the first event has occurred. So for example, two cards are selected without replacing the first card from a standard deck. Find the probability that selecting a king and then selecting a queen. So if you need to, you can Google image search a deck of cards. Kids don't know how to play cards these days. You know, they're playing Candy Crush and all these other things, or PUBG on their mobile devices, whatever it is. Anyway, so whatever your game of choice is, cards is still, a classic thing to play. So two cards are selected without replacing the first card. We want to find the probability of selecting a king and then a queen. Well, if you know about cards, there's 52 total cards, and there's 4 kings and 4 queens. So there's 4 kings, there's 4 queens, and there's 52 total. Just write this on the side so you know what I'm talking about here, just in case you don't know what a deck of cards contains. So we want to find the probability of selecting a king, which is 4 out of 52, times, because we're using a multiplication rule, selecting a queen. Now we have to think, are these independent or not? Do I have to worry about that I selected the king? Well, it says I did not replace the first card. This is without replacement, so I'm not putting the king back. So there's 4 out of 51 cards left that are queens, and I multiply them. And because this is kind of a messy fraction, I'm just going to get a decimal answer for this one. So it's 0.0060, getting a king and a queen. So try to do the rest of this page on your own and see if you can use the multiplication rule and see if you get the same answers that I do. So hopefully you attempted these on your own, and let's go through these. So we want to find the probability of getting heads and a 6. Well, we just discussed, these are independent events. The probability of getting heads is 1/2. The probability of getting a 6 is 1/6. So the probability is 1/12. And I'll just leave that as a fraction. It's a pretty easy fraction to interpret. What about if we have salmon, they swim successfully through a dam, 0.85, find the probability that the 2 salmon successfully swim through the dam. So we want to find the probability we have a success the first time and a success the second time. I'll put a subscript 1 and 2 for the success the first time and the success the second time. And the probability that the first salmon is successful is 0.85. And then once again, we think about independence. Do we think that the first salmon getting through affects the probability of the next salmon getting through? And we don't really have a reason to. There's nothing in the problem that says that there is. So we're just going to multiply by 0.85 again. We're going to assume that the salmon successfully swimming through the dam are independent of each other. So the answer is 0.7225 here. And then the last one, 2 cards are selected from a deck without replacement. Find the probability that they are both hearts. So a heart and then another heart. Now this is without replacement again. So the probability of getting a heart is, and by the way, there's 52 total, remember. If you're curious about hearts, there's 13 hearts in a deck. There's 13 of each suit. Hearts, spades, clubs, and diamonds. They're not paw prints or shuffles, for those of you who like to say that. So 13 out of 52 are hearts. Now, if I already drew a heart, what's the probability of getting another heart? Well, now the numerator and the denominator change, right? There's 12 hearts out of 51 total. And again, this is going to be a messy fraction, so we're going to multiply these and change to a decimal. Okay, so those are some basic probability questions. So let's move on to something a little more difficult on the next page. On the next page, we were talking about a knee surgery, and these 3 problems all go together. And so the probability of a knee surgery is 0.9. Find the probability that 3 knee surgeries are successful. Well, once again, we have no reason to believe, if we're trying to find the probability of 3 successful knee surgeries in a row, so I'll just write 3 S's for this. We can extend this multiplication principle out to multiple events. So probably the first knee surgery successful is 0.9 times probably the second knee surgery is successful is 0.9 and 0.9 for the third. And those probabilities aren't changing because we have no reason to believe that the probability of success is different. And this is 0.729. Okay, let's find the probability that none of the 3 knee surgeries is successful. Well, this is the probability of, instead of writing S prime 3 times, I'm just going to write 3 F's for failure. Well, if the probability of a successful knee surgery, is 0.9, the probability of a failing knee surgery, well, you either succeed or you fail. There's no in between. So these are complements of each other, right? You either get one or the other, and therefore the probability of failure is 0.1. So this is 0.1 times itself 3 times. Which is 0.001. And then the last one, what's the probability that at least one of the 3 knee surgeries is successful? What's the probability that at least one of the 3 knee surgeries is successful? Well, at least one is successful. That's the key there. At least one. Well, what is the complement of at least one? In other words, if you're not getting at least one success, then all the knee surgeries have to be what? Well, failing. Because at least one means that you have at least one success. So if you don't have at least one success, then that means all of them are failing. So 3 failures is the complement. If we want to find the probability of at least one success, we have to do 1 minus, because this is the complement of all failing. And this is a very useful concept, because the probability of all 3 of them failing, right, is going to be 1 minus the probability of at least one success, or what I wrote here, at least one success is the probability of 1 minus the probability of all 3 of them failing. This is the great thing about a complement, because you either have all of them failing or at least one of them are going to be successful. And the nice thing about this is we already figured out the probability of all 3 failing. Is 0.001. So the answer to at least one successful knee surgery is 0.999. Okay. So that's the knee surgery problem. All right. The last problem we're going to do is the middle school problem. And I'm going to give you a chance to read this and answer the questions on your own and see if you can come up with it. So hopefully you read it on your own, but I'll read it one time here and then we'll go over it. So it says more than 15,000 U.S. medical school seniors applied to residency programs in 2007. 93% were matched to a residency position. 74% of the seniors matched to a residency position were matched to one of their top 2 choices. Medical students electronically rank the residency programs in order of preference. The program directors across the United States do the same. The term match refers to the process where a student's preference list and a program director's preference list overlap, resulting in the placement for a student at a residency position. So these last couple sentences really you don't need them. The most important things are there's a 93% chance of a match, and if you are matched, there's a 74% chance of getting a top 2. So if you draw a small tree diagram of this, you're matched or you're not matched. And if you're matched, you get a top 2 or not a top 2. So remember, that's not a 1, that's a little prime for complement. So the probability they're matched is 0.93, and the probability that they get a top 2 is 0.74. So looking at this diagram, let's see if we can answer the questions. Find the probability that a randomly selected senior was matched to a residency position, so they were matched, and it was a top 2 choice. Well, the nice thing about a tree diagram is along the branches we multiply. So we want to find the probability of matching, which is 0.93, and getting a top 2 choice, which is 0.74. And the answer here is 0.6822. Or excuse me, 0.6882. There we go. And that's the probability of getting a residency position, and it was one of the senior's top 2 choices. Okay, and then the next one, find the probability that a randomly selected senior that was matched to a residency position did not get matched with one of the senior's top 2 choices. And this is a little tricky because you have to know what you're actually trying to find the probability of. So it says find the probability that a randomly selected senior that was matched to a residency position. So that was matched to a residency position, this part is what we're given. So we want to find the probability that if they were matched, what is the probability? We're actually trying to find the probability they did not get one of the top 2 choices, which is T prime. So if we go back up to our tree diagram here, I'll zoom out just a little tad. If we go back up to our tree diagram here, we want to find the probability that they did not get a top 2 choice, so this bottom branch here, given that they were matched. So there's no multiplication in this one because we're not trying to find the probability of 2 events occurring in sequence. We already know. It says find a randomly selected senior that was matched to a residency position. We already know they were matched. So if we already know they were matched, what's the probability they did not get one of their top 2 choices? Well, that's this down here. It's going to be 0.26, which came from 1 minus 0.74. Because you either you get a top 2 choice or you don't. So whatever's left over from 0.74, 1 minus 0.74 is the 0.26. That's how we do those. So those are some more conditional probability examples. All right. The last page of this delves into this a little bit more difficulty. So I'm going to actually save that part for later. After section 3.3, I'll post a video about going over this last page and coming back to these notes.